Hey everyone, Lee here. Welcome back to the series where we're mastering the NVIDIA Certified Associate Generative AI Multimodal one question at a time. Today is a big one, as we jump into questions 81 through 100. There are some key concepts in this set, so let's get right to it. Question 81. What is the primary characteristic of a convolutional neural network, CNN, that makes it particularly effective for image recognition tasks? It processes the entire image as a single vector, capturing global relationships between all pixels at once. B. It uses recurrent connections to maintain a memory of previously seen pixels, ideal for sequence analysis. C. It learns a hierarchy of features, with early layers detecting simple patterns like edges and later layers combining them to recognize complex objects. D. It requires significantly more parameters than a fully connected network for the same input image due to its specialized filters. Okay, this question is getting to the core principle of what makes CNNs the go-to tool for almost everything in computer vision. It's basically asking, what's a CNN's superpower? Now let's look at the options. First, we can eliminate the options that describe other types of neural networks. Option A describes how a simple fully connected network might look at an image if you flatten it into one long vector, but this approach loses all the important spatial information. Option B describes a recurrent neural network, RNN, which is designed for sequential data like text or time series, not images. Next, Option D states that CNNs require more parameters, which is the complete opposite of the truth. One of the biggest advantages of a CNN is parameter sharing, which means the same filter is used across the entire image. This dramatically reduces the total number of parameters compared to a fully connected network, making them much more efficient. This leaves us with option C, which is the correct answer. This is the essence of how a CNN sees. The first few layers act like basic visual neurons. They learn to detect very simple things like vertical edges, horizontal lines, corners, or patches of color. Deeper layers take the output from the earlier layers and combine these simple patterns into more complex concepts like textures, or parts of an object like an eye, a nose, or a wheel. The final layers assemble these complex parts to recognize entire objects like a face, a car, or a dog. This hierarchical feature learning, from simple to complex, is the key characteristic that allows a CNN to build a rich and robust understanding of visual content. Question 82. What is the primary architectural feature of an autoencoder, and what is its main goal during training? It consists of an encoder that compresses the input into a latent representation and a decoder that reconstructs the input from this representation, trained to minimize reconstruction error. B. It is a supervised model trained to classify the input into one of several predefined categories using labeled data. C. It comprises a generator that creates data from random noise and a discriminator that distinguishes real data from generated data. D. It uses recurrent layers to process sequences of data, aiming to predict the next item in the sequence. Okay, this question is asking us to identify the fundamental structure and purpose of an autoencoder. It's a key unsupervised learning model, so understanding its design is crucial. Now let's look at the options. First, we can eliminate the options that describe completely different types of models. Option C is a perfect description of a generative adversarial network, GAN, not an autoencoder. Option D describes a recurrent neural network, RNN, which is used for sequential data like text. Option B describes a standard supervised classifier, which requires labeled data and is used for classification tasks. This leaves us with option A, which is the correct answer. This is the textbook definition of an autoencoder. Think of it as a learnable compression system with two key parts. 1. The encoder, this part of the network takes a high-dimensional input like a large image and compresses it down into a much smaller low-dimensional representation. This compressed form is called the latent space or bottleneck. 2. The decoder, this part takes the compressed representation from the bottleneck and does its best to reconstruct the original high-dimensional input from that small amount of information. The entire system is trained by comparing the original input to the reconstructed output. The model's only goal is to make the reconstruction as close to the original as possible, which forces the encoder to learn a very efficient and meaningful way to compress the data. Question 83. A team is developing a responsible AI framework to ensure their models are trustworthy. Which of the following is not considered a core pillar or principle of trustworthy AI? A, fairness and bias mitigation. B, explainability and interpretability. C, robustness and reliability. D, maximization of engagement. Okay, this question is about defining what trustworthy AI really means. It's a broad term, but it's built on a few key ideas or principles that guide responsible AI development. We need to find the one option on the list that is not one of these core principles. Now let's look at the options. The first three options are all essential pillars of trustworthy AI. Fairness and bias mitigation means the AI shouldn't produce discriminatory or unfair outcomes for different groups of people. Explainability and interpretability, B, means the AI shouldn't be a black box. We need to be able to understand how it makes its decisions. And robustness and reliability, C, means the system should be secure, safe, and perform consistently even with unexpected inputs. These principles are all focused on ensuring the AI behaves in a responsible and ethical manner. This leaves us with option D, which is the correct answer, maximization of engagement. This is a business metric, not an ethical principle. The goal of maximizing engagement is to keep users on a platform for as long as possible. This objective can actually be in direct conflict with trustworthiness. For example, an AI optimized only for engagement might learn that promoting sensational, controversial, or false information is the best way to get reactions and keep people clicking. Therefore, it's a business goal, not a pillar of trustworthy AI. Question 84. In the field of trustworthy AI, what is the primary purpose of establishing content authenticity for digital media? To prevent generative AI models from being able to create any content that is not factually correct. B, to ensure that all AI-generated content is automatically deleted from the internet to maintain information purity. C, to provide a verifiable way to track the origin and history, provenance, of a piece of content, helping to distinguish between authentic and manipulated or AI-generated media. D, to create a single, centralized AI model that is the only approved source for generating authentic content. Okay, this question deals with a critical aspect of trustworthy AI, content authenticity. As generative AI becomes more powerful and can create incredibly realistic images, videos, and text, it's more important than ever to have a reliable way to know where our digital media comes from. Now let's look at the options one by one. Option A is incorrect. This describes a goal for the generative model itself, i.e., making it truthful, but it's not what content authenticity is about. Authenticity provides a transparent history for a piece of content, regardless of whether that content is factual or fictional. Option B is incorrect. Content authenticity is not a system for censorship or deleting content. Its goal is to provide transparency and context so that users can make informed decisions about the media they consume, not to remove AI-generated media from the internet. Option C is the correct answer. This is the core mission of content authenticity. The goal is to create a system like the Content Authenticity Initiative, CAI, where a secure, tamper-evident digital nutrition label or birth certificate is attached to a file. This label, often called content credentials, can show you who created the file, when it was created, and what tools, including specific AI models, were used to make or modify it. It's all about providing a clear, verifiable history or provenance to combat misinformation and build trust. Option D is incorrect. This is the opposite of the actual approach. Content authenticity relies on an open, decentralized standard that any tool or creator can choose to adopt. The idea is to create a widespread ecosystem of trust, not to centralize and control content creation. Question 85. A data science team has trained a new recommendation model that shows higher offline accuracy than the current production model. What is the primary reason for conducting an A/B test before fully deploying the new model? A, to further train the new model on live user data. B, to determine which model has a lower computational cost and inference latency. C, to measure the new model's causal impact on key business metrics, e.g., user engagement, conversion rates, in a live production environment. D. To recalculate offline metrics like accuracy and F1 score using real-world data. Okay, this question is about a crucial step in the machine learning lifecycle, A/B testing. It's one thing for a model to look good in the lab on a static dataset, but the real test is how it performs with live users in the real world. B testing is how we measure that. Now let's look at the options one by one. Option A is incorrect. This confuses testing with training. An A/B test is a controlled experiment designed to evaluate a finished model's performance and impact, not a method to continue training it with live data. Option B is incorrect. While monitoring technical performance metrics like latency is an important part of any deployment, it is not the primary reason for conducting an A/B test. The main goal is to understand the model's effect on user behavior and business outcomes, which is a different kind of measurement. Option C is the correct answer. This is the core purpose of A/B testing in a business context. Offline metrics like accuracy don't always translate to the desired real-world impact. An A/B test is the gold standard for scientifically measuring if your new model actually causes an improvement in the things the business cares about, such as getting more users to click a recommended item, buy a product, or spend more time on the site. Provides the ground truth for a model's business value. Option D is incorrect. This misses the key distinction between offline and online evaluation. The purpose of an A/B test is to move beyond these model-centric metrics like accuracy and measure the impact on user-centric and business-centric KPIs, which are what truly matter in a production system. Question 86. A developer is building a high-throughput application that needs to process thousands of images per second using a model deployed on NVIDIA Triton Inference Server. To achieve the highest possible throughput, what is the primary advantage of using Triton's support for asynchronous inference requests? It allows the client to send many requests without waiting for each one to complete, which maximizes GPU utilization and overall system throughput. B. It reduces the latency of each individual inference request to its absolute minimum. C. It automatically quantizes the model to a lower precision for faster execution. D. It guarantees that requests are processed and returned in the exact order they are sent. Okay, this question is about a key performance feature of NVIDIA's Triton Inference Server. When you're building a system that needs to handle a huge volume of requests, how you send those requests to the server makes a big difference. Let's look at the advantage of the asynchronous approach. Now let's look at the options one by one. Option A is the correct answer. This is the core benefit of asynchronous programming. With a traditional synchronous approach, a client sends one request, waits for the response, gets the response, and only then sends the next request. This creates a lot of idle time. With asynchronous requests, the client can fire off 100 requests in a rapid burst without waiting for any of them to finish. This builds up a constant queue of work for the Triton server, which ensures the powerful GPU is always busy processing something. This continuous utilization is what leads to maximum system throughput, which is the total number of requests handled over time. Option B is incorrect. This is a common misconception. Asynchronous requests do not necessarily reduce the latency of a single request. The time it takes for one specific request to be processed and returned might be the same or even slightly longer. The real win is in the overall system efficiency and the total number of requests processed per second, throughput, not the speed of an individual request. Option C is incorrect. Quantization is a very important model optimization technique that you apply to your model before deploying it. It's a great way to improve performance, but it is a separate process and is not a feature of the asynchronous request-response pattern. Option D is incorrect. In fact, the opposite is often true. Because requests are processed in parallel on the server and might take slightly different amounts of time, an asynchronous system does not guarantee that the responses will arrive in the same order the requests were sent. If strict ordering is required, a different feature like Triton's sequence batching must be used. Question 87. An AI development team is working on several different projects. Which of the following correctly pairs a project's primary evaluation need with the most appropriate metric? Select 2. For a spam email detection model where 99% of emails are not spam, the F1 score is used to provide a balanced measure of performance. B. For a model that predicts house prices, accuracy is used to measure the percentage of exactly correct price predictions. C. For an automated system that generates English captions for German videos, the BLEU score is used to compare the generated English captions to human-written ones. D. For a generative model that creates new images of faces, the F1 score is used to measure the realism of the faces. E. For a model that groups customers into segments, the R-squared score is used to measure the quality of the clusters. Okay, this question is a practical test of your knowledge of evaluation metrics. It's not enough to just know the definition of a metric. You need to know which tool to use for which job. Here, we need to find the two scenarios where the project and the chosen metric are a perfect match. Now let's look at the options one by one. Option A is a correct answer. This describes a classic imbalanced classification problem. If a model simply predicted not spam every time, it would achieve 99% accuracy, which sounds fantastic but is completely useless because it never catches any spam. The F1 score, which is the harmonic mean of precision and recall, provides a much more realistic and useful measure of the model's performance on the rare, positive class, in this case, spam. Option B is incorrect. Predicting a house price is a regression task, where the output is a continuous numerical value, not a classification task. You cannot use accuracy for this. The appropriate metrics would be something like mean squared error, MSE, or root mean squared error, RMSE, to measure the average error of the price predictions. Option C is also a correct answer. The task of generating English text from a German source, whether text or video, is fundamentally a translation or sequence-to-sequence task. The BLEU score is a standard and widely used metric for this purpose. It evaluates the quality of the machine-generated text by comparing its word and phrase overlap with one or more high-quality, human-written reference texts. Option D is incorrect. The F1 score is a metric for classification tasks. Evaluating the quality or realism of generated images requires specialized computer vision metrics, such as the Freshet inception distance, FID, or the inception score, IS. Option E is incorrect. The task of grouping customers into segments is known as clustering. The quality of clusters is measured by metrics like the silhouette score or the Davies-Bouldin index. R-squared is a metric used to evaluate how well a regression model fits the data, not for evaluating clustering performance. Question 88. A data analyst is working with a dataset from an e-commerce website. They want to visualize the distribution of customer ages to understand the age demographics of their user base. Which type of chart is most suitable for this specific task? A line chart, B, a bar chart, C, a histogram, D, a pie chart. Okay, this question is about a fundamental skill in data analytics, choosing the right tool for the job. In this case, the tools are different types of charts, and the job is to visualize a specific aspect of a dataset. We need to pick the best chart for understanding the distribution of customer ages. Now let's look at the options one by one. Option A is incorrect. A line chart is used to show trends over a continuous interval, most commonly time. For example, you would use a line chart to show how the total number of users has grown each month for the past 5 years. It is not used to show the distribution of a single variable like age at one point in time. Option B is incorrect, though it's a common point of confusion. A bar chart is best for comparing values across discrete, separate categories. For example, you would use a bar chart to compare total sales across different product categories like electronics, books, and clothing. While you could manually group ages into categories and use a bar chart, the specific tool designed for showing the frequency distribution of a single, continuous variable is a histogram. Option C is the correct answer. A histogram is the perfect tool for this task. It takes a single continuous numerical variable, like age, separates it into a series of intervals or bins, e.g. 20 to 24 years old, 25 to 29 years old, etc., and then plots the frequency, the number of customers, that fall into each bin. This gives you an immediate and clear visual representation of the age distribution, showing you which age groups are most common and how the ages are spread out. Option D is incorrect. A pie chart is used to show the proportions of a whole. For example, you could use a pie chart to show what percentage of your total sales comes from each country. It is not effective for visualizing the distribution of a continuous variable like age. Question 89. In a standard transformer architecture, which two of the following statements accurately describe how the self-attention mechanism processes an input sequence and understands word order? Select 2. It dynamically calculates the importance of all other tokens in the sequence for each token, using query, key, and value matrices. B. It processes the sequence token by token, passing a hidden state from one step to the next to remember the context. C. It uses a fixed-size convolutional filter to capture local context around each token. D. It has no built-in sense of word order, so positional encodings must be added to the input embeddings to provide information about the sequence. E. It can only attend to the immediately preceding token in the sequence, which limits its context window. Okay, this question gets to the heart of the transformer architecture and its most important innovation, the self-attention mechanism. We need to identify two true statements about how it works and how it handles the order of words in a sentence. Now let's look at the options one by one. Option A is a correct answer. This is a perfect description of the core attention process. For every single word in a sentence, the model generates three vectors: a query, representing the current word's question, what should I pay attention to? A key, representing that word's content, here's what I am, and a value also representing that word's content. By comparing one word's query to every other word's key, the model calculates attention scores that determine how much importance or focus to place on each word's value when creating its final representation. Option B is incorrect. This describes the sequential, step-by-step process of a recurrent neural network, RNN. A key advantage of the transformer's self-attention mechanism is that it processes all tokens in the sequence in parallel, making it much more efficient. Option C is incorrect. This describes the mechanism of a convolutional neural network, CNN, which uses fixed filters or kernels to look at local windows of data. Self-attention, by contrast, can create dynamic connections between any two words in the sequence, regardless of their distance. Option D is also a correct answer. This is a crucial and often misunderstood point about the self-attention mechanism. By itself, the mechanism is permutation invariant, meaning it doesn't have an inherent understanding of word order. To solve this, the transformer architecture adds a unique, positional encoding vector to each word's embedding before it enters the attention layers. This explicitly injects information about the position of each word in the sequence. Option E is incorrect. This is the exact opposite of self-attention's main benefit. Its power lies in its ability to create direct connections between any two tokens in the sequence, no matter how far apart they are. This allows it to capture the long-range dependencies that older architectures like simple RNNs struggled with. Question 90. An enterprise is using a large generative AI model to create marketing copy and customer-facing communications. What is the primary purpose of implementing guardrails as part of a trustworthy AI strategy for this application? A. To accelerate the model's inference speed by simplifying the output. B. To enforce policies and ensure the generated content is on topic, safe, and aligned with the company's brand and ethical guidelines. C. To track the provenance of the generated content using a system like the Content Authenticity Initiative. D. To increase the creativity and diversity of the model's output by using a higher temperature setting. Okay, this question tackles a crucial topic for any business looking to use generative AI. How do you ensure the AI's creative output is safe, on-brand, and appropriate for your customers? This is where the concept of guardrails comes in. Now let's look at the options one by one. Option A is incorrect. Guardrails are a safety and quality check, which typically adds a small amount of processing time or latency. Their goal is to improve the trustworthiness and safety of the output, not the raw speed of inference. Option B is the correct answer. This is the perfect description of AI guardrails. Think of them as an automated content moderation layer that sits around the generative model. They can check the user's prompt on the way in to block inappropriate requests, and they check the AI's generated response on the way out before it's shown to the user. Their job is to enforce a set of rules, for example, do not use offensive language, do not discuss off-topic subjects, and ensure the tone is consistent with our brand voice. This is essential for using generative AI safely in a business context. Option C is incorrect. This describes content authenticity, which is another important pillar of trustworthy AI. Content authenticity is about providing a verifiable history or provenance of a piece of content. Guardrails, on the other hand, are about actively monitoring and controlling the content of a conversation in real time to ensure it is appropriate. Option D is incorrect. This is the opposite of a guardrails function. Increasing the temperature makes the output more random and less controlled. Guardrails are designed to add control and constraints to the generation process to ensure it stays within safe and desirable boundaries. Question 91. In the architecture of a large multimodal model, like a visual language model, what is the primary function of a pre-trained vision encoder, such as the one from CLIP, in relation to the large language model, LLM? A. To replace the LLM's existing text-based vocabulary with a new set of visual words. B. To convert an input image into a sequence of embeddings or visual tokens that the LLM can process alongside text tokens, effectively allowing the LLM to see. C. To fine-tune the LLM by first generating captions for a large image dataset, which are then used as new training data. D. To act as a final filter that checks if the LLM's text output is visually consistent with the input image. Okay, this question explores the powerful combination of vision models like CLIP and large language models. We know LLMs are amazing with text, but how do we give them the ability to see and understand images? This question asks about the specific role of the vision encoder in that process. Now let's look at the options one by one. Option A is incorrect. The vision encoder doesn't replace or erase the LLM's powerful, pre-existing language capabilities. Instead, it provides a new, additional source of information that complements and works together with the text. Option B is the correct answer. This is the core concept of how modern multimodal LLMs work. The pre-trained vision encoder acts as the eyes of the system. It looks at an input image and effectively translates it into a sequence of numerical representations, embeddings. These can be thought of as visual tokens. These visual tokens are then fed into the LLM's processing stream right alongside the regular text tokens from a prompt. This allows the LLM, which is already an expert at understanding sequences and relationships between tokens, to learn to read the visual information and reason about it in the context of the text. Option C is incorrect. While you could use a model to generate captions to create a training dataset, this describes a data preparation strategy. It does not describe the direct architectural role of the vision encoder during the model's actual operation when it receives an image as input. Option D is incorrect. This describes a potential post-processing or verification step that could happen after the LLM has generated its response. The primary function of the vision encoder is to provide the visual information as an input to the LLM's reasoning process, not to check its output after the fact. Question 92. During the iterative denoising process of a text-to-image diffusion model, how is the pre-trained CLIP model's text embedding primarily used? It serves as a target semantic vector, and at each step, the model steers the denoising process to make the image embedding closer to this target. B. It is used only once at the beginning of the process to select an appropriate initial random noise pattern. C. It functions as a final validation check, rejecting any completed images that do not have a high similarity score with the prompt. D. It directly modifies the weights of the diffusion model's UNet in real time to better specialize it for the given prompt. Okay, this question dives a bit deeper into the partnership between CLIP and diffusion models. We know CLIP acts as the director, but this question asks how exactly it gives directions to the artist, the diffusion model, while it's in the middle of painting. Now let's look at the options one by one. Option A is the correct answer. The CLIP text encoder creates a target destination in a shared meaning space that represents the prompt. The diffusion process starts with a random image, pure noise, that is far away from this destination. At every single denoising step, the system steers the process in a direction that moves the image's representation closer to the CLIP text embedding. It's a continuous process of course correction, guided at every step by the CLIP embedding, that ensures the final image is a good match for the prompt. Option B is incorrect. The guidance from clip is not a one-time event at the start. It is a crucial signal that is applied repeatedly throughout the entire generation process to keep the image on track. Option C is incorrect. This describes a form of rejection sampling, which would happen after the entire generation process is finished. While you could do this, it's very inefficient. Clip's primary role is to be integrated within the generation loop to guide the process towards a good result, not just to filter out bad results at the end. Option D is incorrect. This describes a form of real-time training or fine-tuning. During inference, the weights of the diffusion model's U-Net are frozen. The clip embedding guides the output of the model at each step, but it does not change the model's underlying learned parameters. Question 93. In a conditional diffusion model used for text-to-image generation, how is the context embedding, typically from a model like clip, used to control the final image output? It is used to select a pre-existing image from a large database that best matches the context. B. It replaces the initial random noise, providing a structured starting point for the diffusion process. C. It is fed into the denoising U-Net at each step, providing guidance that influences the noise prediction to create an image matching the context. D. It acts as a final loss function to score the semantic similarity of the generated image after the process is complete. Okay, this question is about how we take a powerful but inherently random image generator, a diffusion model, and give it specific instructions to control its output. An unconditional diffusion model will just create a random image from its training domain, e.g., a random face. We want to tell it what to create, and this is where context embeddings come in. Now let's look at the options one by one. Option A is incorrect. This describes an image retrieval system, which finds an existing image. Diffusion models are generative. They create entirely new, original images from scratch, not just search for them. Option B is incorrect. This is a common misunderstanding. The diffusion process must start from a canvas of pure random noise. The context embedding is not the starting point itself. It's the map, or guide, that is used throughout the journey to transform that noise into a coherent image. Option C is the correct answer. The core of a diffusion model is a U-Net that predicts the noise in an image at each step. In a conditional model, the context embedding from the text prompt is fed as an additional input to this U-Net at every single step. The U-Net then learns to make its noise prediction conditional on that context. In essence, the context embedding tells the U-Net, don't just remove any noise. Remove noise in a way that will make the image look like what I've described. This continuous guidance is what allows us to control the final output. Option D is incorrect. This confuses the generation process with an evaluation step that happens afterward. The context embedding is an active input that is used during the iterative denoising process to create the image. It is not a metric used to score the final image after it has already been made. Question 94. When a system uses the pre-trained clip model to generate images from text prompts, what is the specific role of clip in the overall architecture? It functions as a standalone generative model that directly converts text embeddings into image pixels. B. It acts as a guide or a perceptual loss function, steering a separate generative model, like a GAN or diffusion model, to produce images that are semantically aligned with the text prompt. C. It is only used to pre-process the text prompt into tokens before another model generates the image. D. It is used after the image is generated to create a text caption, which is then compared to the original prompt for validation. Okay, this question tackles a very common but important point of confusion about the clip model. While we associate clip with amazing text-to-image generation, its specific job in that process is often misunderstood. Let's clarify its exact role. Now let's look at the options one by one. Option A is incorrect. This is the most common misconception. The clip model itself does not generate any pixels. It is an expert at understanding the relationship between text and images, but it is not a generative model on its own. Option B is the correct answer. This perfectly describes clip's role. It acts as the director or art critic for another, separate generative model, like a GAN or a diffusion model. The generative model creates an image, and Clip looks at both that generated image and the original text prompt and provides a score of how well they match semantically. This score is then used as a signal to continuously update and steer the generator, forcing it to create images that are a better and better match for the text. Clip provides the crucial guidance, but another model does the actual generating. Option C is incorrect. While Clip's text encoder is used to process the prompt, its role is far more active than just simple pre-processing. The embedding it creates is used continuously throughout the generation process to guide the outcome, not just at the very beginning. Option D is incorrect. This describes using Clip as a final evaluation metric after the image has been created. While you can do this, its primary role in a text-to-image system is to be an active part of the generation loop itself, not just a judge at the end. Question 95. Which of the following options represents the most logical and standard sequence of steps in a typical machine learning project workflow? Model training dash, data collection dash, model evaluation dash, data preparation dash, deployment. B. Data collection dash, model training dash, data preparation dash, model evaluation dash, deployment. C. Data collection dash, data preparation dash, model training dash, model evaluation dash, deployment. D. Data collection dash, data preparation dash, deployment dash, model training dash, model evaluation. Okay, this question is about the fundamental workflow of a machine learning project. Just like building a house, you have to follow a logical sequence of steps to be successful. We need to find the option that lays out these steps in the correct and standard order. Now let's look at the options one by one. Option A is incorrect. This sequence is completely scrambled. The most obvious error is that it starts with training the model. You cannot possibly train a model before you have collected and prepared the data for it. Option B is incorrect. This option correctly starts with data collection, but then it makes a critical mistake. It tries to train the model before preparing the data. Raw data from the real world is often messy, contains errors or missing values, and is not in the correct format for a model to learn from. You must always prepare, clean, and transform your data before the training step. Option C is the correct answer. This represents the standard logical flow of a typical machine learning project. 1. First, you data collection, gather all the raw data you need. 2. Next, you data preparation, clean the data, handle missing values, perform feature engineering, and split it into training, validation, and test sets. 3. Then, you use this prepared data for model training. 4. After training, you use the test set for model evaluation to see how well it performs on unseen data. 5. Finally, if the model's performance is acceptable, you proceed to deployment, putting it into a production environment. Option D is incorrect. This sequence has a major logical flaw. It attempts to deploy the model before it has been trained or evaluated. You would never put an untrained and untested model into a live application for users to interact with. Question 96. What is the primary motivation for using mixed precision training, e.g., using both FP16 and FP32, when training large deep learning models on modern NVIDIA GPUs? A. To prevent the model from overfitting by adding noise to the gradient calculations. B. To significantly accelerate training speed and reduce memory consumption by leveraging hardware-optimized, lower precision computations. C. To make the model's predictions more interpretable and explainable to stakeholders. D. To ensure perfect numerical stability and completely avoid any possibility of vanishing or exploding gradients. Okay, this question is about a very important technique for making the training of massive AI models practical, mixed precision training. It's a clever trick to get a huge speed up without sacrificing the quality of your final model. Let's look at why it's used. Now let's look at the options one by one. Option A is incorrect. The primary goal of mixed precision training is not regularization. While using lower precision might introduce a very small amount of numerical noise, dedicated techniques like dropout and weight decay are the proper tools for preventing overfitting. Option B is the correct answer. This is exactly why mixed precision is so widely used. Modern NVIDIA GPUs have specialized hardware called tensor cores that are designed to perform mathematical operations with 16-bit floating point numbers, FP16, or half precision, dramatically faster than with the standard 32-bit numbers, FP32, or single precision. Using FP16 also cuts the memory required to store weights and activations in half. Mixed precision training cleverly performs the bulk of the heavy computations in fast FP16, while keeping a master copy of the weights in the more stable FP32. This gives you a massive boost in training speed and allows you to train larger models or use larger batch sizes. Option C is incorrect. The numerical precision used for the model's weights has no direct connection to its explainability. Interpretability is a separate field of study addressed by techniques like SHAP or LIME. Option D is incorrect. This is a subtle but important point. Using only low-precision numbers can actually increase the risk of numerical problems like vanishing gradients. The mixed aspect is the key. It's a strategy designed to get the speed benefits of FP16 while still using FP32 for sensitive parts of the calculation, like accumulating updates, in order to maintain numerical stability, not to guarantee it perfectly. Question 97. Which of the following are prominent examples or primary use cases of decoder-based large language model architectures? Select 3. A generative pre-trained transformer GPT models used for tasks like conversational AI and creative text generation. B. Generative adversarial networks, GANs, used for generating realistic images. C. Sequence-to-sequence models like BART, which use a decoder to perform tasks like text summarization. D. The stable diffusion model used for text-to-image synthesis. E. Code generation, where the model produces syntactically correct code based on a natural language prompt. F. Encoder-only models like BERT, used for tasks like sentiment analysis and named entity recognition. Okay, this question is about identifying the family of models and tasks that rely on a decoder architecture. In the world of transformers, decoders are the specialists in generation. Their job is to create new sequences of text, code, or other data in an autoregressive way. Now let's look at the options one by one. Option A is a correct answer. The G in GPT stands for generative, and it is the most famous example of a decoder-only architecture. It is designed specifically for open-ended text generation, which is why it excels at tasks like building chatbots, like ChatGPT, and creative writing. Option B is incorrect. Generative adversarial networks, GANs, are a completely different type of generative model. They are composed of a generator and a discriminator that work in opposition to each other and are not considered decoder-based LLMs. Option C is a correct answer. BART is a classic example of an encoder-decoder architecture. The encoder reads and understands an input text, and the decoder's job is to generate the new output text. This makes it extremely effective for sequence-to-sequence tasks like taking a long article and generating a concise summary. Option D is incorrect. Stable diffusion is a type of diffusion model, which is another category of generative model distinct from LLMs. While it uses a text encoder, like CLIP, for guidance, its core generative component is a UNet, not a transformer decoder. Option E is a correct answer. This is a primary application of modern decoder-based LLMs. Models like OpenAI's Codex or GitHub's Copilot are large language models with decoder architectures that have been trained specifically on vast amounts of code, enabling them to generate new, functional code from natural language descriptions. Option F is incorrect. BERT is the classic example of an encoder-only model. Its architecture is designed to read and understand the full context of a sentence to produce rich representations for tasks like classification, e.g., sentiment analysis, or extraction, e.g., named entity recognition. But it is not built for generating new, free-form text. Question 98. In an encoder-decoder transformer model like T5, text-to-text transfer transformer, what are the distinct primary responsibilities of the encoder and the decoder? A. The encoder generates the output sequence, while the decoder's main role is to classify the input. B. Both the encoder and decoder work in parallel to generate different parts of the final output sequence. C. The encoder creates a contextual representation of the entire input sequence, and the decoder uses that representation to autoregressively generate the output sequence. D. The encoder processes the input sequence one token at a time with a hidden state, and the decoder reverses this process. Okay, this question is about the classic two-part structure of many famous transformer models, the encoder-decoder architecture. Think of it as a system with two specialized components, one for understanding an input and one for writing an output. We need to correctly identify the role of each part. Now let's look at the options one by one. Option A is incorrect. This has the roles completely backward. The decoder is the part that generates or writes the output sequence, while the encoder is the part that reads or understands the input. Option B is incorrect. The process is sequential, not parallel. The encoder must first completely process the input to create a meaningful representation before the decoder can begin its task of generating the output. Option C is the correct answer. This is the perfect description of the workflow. The encoder acts like a reader. It looks at the entire input sequence at once, e.g., an English sentence for translation, and uses its self-attention mechanism to create a rich, numerical representation that captures the full meaning and context of that sentence. The decoder acts like a writer. It takes the rich representation from the encoder as its starting instruction, and then, one word at a time, autoregressively, it generates the new output sequence, e.g., the translated sentence in German. Option D is incorrect. This describes the mechanics of a recurrent neural network, RNN, which processes data sequentially, passing a hidden state from one step to the next. A key advantage of the transformer's encoder is that it can look at all the input tokens at the same time, which is more powerful for capturing context. Question 99. Which of the following statements most accurately describes the range of applications for the transformer architecture in modern AI? A. The transformer architecture is exclusively designed for natural language processing, NLP, tasks and is not suitable for other data types like images or audio. B. Transformers are effective for analyzing text and images, but their architecture cannot be applied to sequential audio data. C. Transformers are only useful for generative tasks like creating text and cannot be used for analytical tasks like classification. D. While originally designed for text, the transformer has become a foundational architecture for various modalities, including computer vision, speech recognition, and multimodal tasks. Okay, this question is about the incredible versatility of the transformer architecture. It originally became famous for its amazing performance on text-based tasks, but its influence has spread far beyond that. We need to identify the statement that best captures its wide range of capabilities. Now let's look at the options one by one. Option A is incorrect. This is a common misconception based on the transformer's origins with the "attention is all you need" paper for machine translation. While it was a revolution for NLP, researchers quickly realized its core mechanism, self-attention, could be adapted for many other data types. Option B is incorrect. This statement is only half right. Vision transformers, VITs, proved that the architecture works well for images. However, state-of-the-art speech recognition models like OpenAI's Whisper are also built entirely on the transformer architecture, demonstrating that it is highly effective for processing audio data as well. Option C is incorrect. This confuses the different types of transformer models. Decoder-based models like GPT are indeed excellent for generative tasks. However, encoder-based models like BERT are specifically designed and widely used for analytical tasks like text classification, sentiment analysis, and named entity recognition. Option D is the correct answer. This is the most accurate and complete statement. The transformer began in NLP, but its fundamental design for finding relationships in sequential data has proven to be a general-purpose breakthrough. It has been successfully adapted to computer vision with vision transformers, VITs, that treat image patches as a sequence, speech recognition with models like Whisper that process audio spectrograms as a sequence, multimodal models where it's used as a powerful way to fuse and find relationships between sequences of data from different sources, e.g., text and images. It is truly a foundational architecture for much of modern AI. Question 100. Studies have shown that some commercial facial recognition systems have higher error rates for women and people of color, particularly dark-skinned women, compared to white men. What is the most common and fundamental reason for this demographic bias? The algorithms are inherently incapable of processing darker skin tones due to physical limitations of camera sensors. B. The training datasets used to build the models were not diverse and were predominantly composed of images of lighter-skinned males. C. The models intentionally prioritize accuracy for the largest demographic group to maximize overall performance metrics. D. Different demographic groups have facial structures that are too complex for current neural network architectures to understand. Okay, this is a very important question that deals with a real-world ethical challenge in AI: bias in facial recognition. It's a well-known problem that these systems can perform differently for different groups of people, and this question asks for the main reason why. Now let's look at the options one by one. Option A is incorrect. While poor lighting can affect any camera, this isn't a fundamental limitation of the sensor technology itself. The core problem lies in the software and the data it was trained on, not the hardware's inability to see certain skin tones. Option B is the correct answer. This is the root cause of the problem, often referred to as biased in, biased out. The performance of an AI model is a direct reflection of the data it was trained on. Historically, the large datasets used to train many foundational facial recognition models were heavily skewed and did not have balanced representation across different demographics. They often contained a disproportionately high number of images of white men. As a result, the model becomes an expert at recognizing this group but performs poorly on underrepresented groups because it has seen far fewer examples to learn from. Option C is incorrect. While the outcome might look like this, the bias is rarely intentional. It's typically an unintentional consequence of using imbalanced data. The developers didn't set out to create a biased model. They often failed to use a dataset that was truly representative of the global population the model would be used on. Option D is incorrect. This statement is false. Modern neural network architectures are incredibly powerful and are fully capable of learning to recognize faces from all demographic groups equally well. The failure is not in the architecture's capability, but in the data it is given to learn from. Thanks for watching. If you found this video interesting and helpful, please like, share, and subscribe to our channel. See you in the next video. Happy learning!